Okay. So
Hi, my name is Michael.
I am Sucha, and
We are the Tan Kids.
So just some background. Infrasound is low frequency sound and ultrasound is high frequency sound. We're using an ultrasonic sensor for our project using Raspberry Pi. An ultrasonic sensor senses an object's range using ultrasound reflection. It also calculates the time it takes to reflect ultrasound waves between a sensor and a solid object. As far as the code, we're using trig, which triggers the sensor to send an ultrasonic pulse. We're using echo, which is the sensor output signal, to send a pulse back to the sensor. When we were working on a project, we used something called SDLC, which stands for System Development Lifecycle. We'll go through the steps with you guys.
Okay. First part of SDLC is goal. Our program, for our goal, we wanted to see how far to program our ultrasonic sensor, determine how far it'll read the distance.
Our second part was design, so we had to plan the layout of our circuit board and also decide where to place the resistors and the wires.
Now the build was the assembly of all the parts. We wanted to see where the wires, the cables, and the ultrasonic sensor were.
The next step was programming, and this is where the coding comes in.
Okay, so now I'm going to go over the code. So our first line of code is we had to import Raspberry Pi into Python, and then we also imported time. So now we make time as a factor as well. We labeled trig as our pin 4 and echo as our pin 27. We're having a couple difficulties with our pins, so then we changed it to GPIO.BCM instead of the other pins that are used in GPIO.board. But we figured it out. We made trig our output, echo our input. So trig goes out and receives a signal, echo brings it back. And then we first activated it, we had trig go on, so GPIO.out, and then echo GPIO.in, so defining as our output input. Then we set our trig, and then we put a delay time.sleep, and then GPIO.output trig.true, comma true. We also put a delay after that. And then we used the physics equation, modified that a bit to determine how far the object is. We divide that number by 2, and that'll tell us how far the object is from the ultrasonic sensor. And then we programmed it to tell us the distance in centimeters, and that's all the code.
When we programmed it, we had to test it. We had to test it multiple times to see if it was accurately reading. Then we ran into a few difficulties. So then we had to rethink.
So when we came to rethinking, we realized that we had to change the sensor, the pins, and the code. And finally, we got it to work.
And then at the end of it, we played with it at the end to see if it was reading properly. And we put our hand in front of the sensor to make sure we're getting the proper numbers.
So that is SDLC.
My hand gets closer, the numbers become seemingly smaller and smaller and smaller. As I go farther, the numbers increase.
But letting go of the right key will stop you from moving.
You just have to talk louder.
So this is our programming for the 3-motor chassis. As you can see, we use straight move blocks, but also different kinds of turns, including the pivot turn and the one-wheel turn. We also had a reverse move block. For the straight move blocks, we use different rotations, the rotations of the wheels. But when it came to turns, for the turn move blocks, we used degrees to get it more precise. Right here. The degrees makes it more precise. And that's our program.
Okay, first scene, so our technology, we have the NXT, the motors, engineering, we have to put it all together with the wires, the motors, it's basically assembly of it. Art, just have to make it look symmetrical and aesthetic as possible. And mathematics, we have to do the degrees, the rotations on it to get it to the angle that we want. And then soft skills, we have to collaborate with our partner to get the parts we need.